So we have motivated the use of DAGs by saying that they are useful for representing tasks and dependencies. And one of the things that we need to do in a DAG, in a directed acyclic graph, is to arrange the vertices in a list that respects the dependencies. So we said this is a topological sort. In a topological sort of the vertices, we sequentially list out the vertices in such a way that every time there is a directed edge from I to j, I must appear before j in the sequence that we list out. So in terms of the applications that we are thinking of, if we think of these as tasks and dependencies, then this type of a topological sort represents a feasible schedule, a schedule in which no task appears before all the tasks it depends on are already completed, right? So when you come to do something, everything you need to do before that is already done. So the first thing to notice is that if you have cycles, then you cannot do this, right? If you have a graph with directed cycles, we informally argued that if I depend on somebody else to finish and somebody else depends on me to finish, then we can't do anything because we're waiting for each other to finish. But formally, let us see what it means. So in the topological sort, it's not just for every edge, right? For every edge I comma j, it is clear that topological sort requires I to appear before j. But in general, if I have a path of dependencies, if I depends on k and k depends on j, then I must come before k and k must come before j. So therefore, transitively, I must come before j. So anytime there is a path from I to j, I must be listed before j. So now if I have a cycle in a directed graph, it means that I can go from some I to some other j. So remember, a cycle cannot be just something which goes from I to I without going to any other vertex. We need to go at least across one edge. So I must go from I to some other vertex j and then come back. So there is a path from I to j and a path back from j to I. Now by the previous requirement, if there is a path from I to j, then the topological sort is obliged to put I before j. But since there is also a path from j to I, then we have to put j before I. But clearly in a given sequence, either I can come before j or j can come before I. We cannot have both these constraints satisfied in the sequence, and therefore this would be impossible. So that's why if we have a cycle of dependencies, there is no way to order them in a feasible sequence such that each task appears only after everything it depends on has happened before. So what we are going to do now is to show the other side of this. So what we said is, if it is not a directed acyclic graph, so it is directed but with cycles, then topological sorting is always impossible. On the other hand, what we need to argue is that if you give me a feasible set of constraints in the sense that there are no cycles, there are no cyclic dependencies, it is a DAG, then I will always be able to complete it in some reasonable order. So every DAG can be topologically sorted. So how would we go about doing this? So clearly I have to begin somewhere, right? So the first thing I have to do is list out a task which has no dependencies. It doesn't require anything else to be done. So there must be a vertex with no dependencies. There may be more than one. If you look at this graph on the right, we see that 0 has no incoming edges. So 0 doesn't depend on anything. 1 has no incoming edges. So I could start with 0 or I could start with 1. But in general, I need to find such a vertex which has no incoming dependencies to start with. Now as I complete the dependencies, a later vertex which depends on a few things now becomes available because everything that needed to be done before that is done. So as long as we can find vertices whose dependencies have already been listed, we can then list these. So this is our general strategy, right? So we first start with something which has no dependencies, and every time we have a dependency satisfied, we strike it off the list. So then vertices which do have dependencies, eventually all the dependencies have already been listed and then I can list them. So in order to apply the strategy, we need to of course guarantee that there will be a starting vertex with no dependencies. Otherwise there's no way we can start. And then we also have to guarantee that eventually every vertex which has dependencies will find all those dependencies listed out, right? So we have to make sure that every vertex, remember that we said that whenever we have a DAG, we can do a topological sort. This is our claim. And this our strategy above says that we are going to do this by starting with a vertex with no dependencies. So first we have to show that such a vertex exists. And then we have to argue that as we progress, we are definitely going to eliminate all the vertices into our list and finally finish by doing all the tasks or listing them all out in this topological sort, right? So we need to somehow justify these claims in order to proceed with this strategy. So remember that in a directed graph, we talk about the in degree and the out degree of a vertex as opposed to just the degree. So in an undirected graph, the degree of a vertex refers to the number of edges which are incident on that vertex. How many edges have that vertex as an endpoint? But in a directed graph, these edges could either come in or they could go out. So the in degree is how many edges are pointing into a vertex V. What we are looking for is a vertex with no dependencies. That means nothing is pointing into it. V does not depend on anything, so there is no edge of the form u comma v. So why must there be such a vertex, right? So the claim is that every DAG must have such a vertex with in degree 0. So let's suppose we have vertices with in degree not 0. So pick any one. So we start with a vertex V which has in degree greater than 0. Since it has in degree greater than 0, there is at least one edge coming into that vertex. So we can follow that edge backwards and go to a preceding vertex, right? So we can go back from V to a preceding vertex. So let us say, supposing we start here, we say that this vertex, right, has some incoming edge. So I go across this vertex, I go backwards, right, and I come to this vertex. Now I say, oh, this vertex also has a non-zero number of incoming things. It has in degree greater than 0, right? So I will keep doing that. So I'll start here, then I'll go back here, right, and then maybe I'll go back here, and then maybe I'll go back here, and then I stop because I cannot go back any further. So in this particular case, this graph is acyclic and I have stopped at 0 by starting at 6. If I started at 7, I could follow a different path. For example, I could go from 7, I could go to say 4 and then 0, or from 6 I could have gone from 5 to 2 to 1 and so on. But whichever way I do it, eventually all these paths will have to stop. And why is this the case? Well, supposing I start at some V, let me call it V1 or V0 if you want, right? Then I come back to another vertex which is V1. And then I can't stop because V1 has in degree greater than 0, so I have to go back to another vertex which is V2. Now, if I hit the same vertex again, then I have a cycle. So let me assume that V1 is different from V0 and V2 is different from V1 and V0. So I'm continuously hitting new vertices as I go along. If I don't hit a new vertex every time I go backwards, I've already found a cycle and I know this graph has no cycles. But on the other hand, this graph has only n vertices. So if I start at V0 and I do one step, I get back to V1. If I do 2 steps, I get to V2. So if I do n minus 1 steps, I have reached Vn minus 1. Right? So after I have done this, if I do it one more time, if I do an nth step backwards, then I cannot find a new vertex anymore which I have not seen before, because all the n vertices in my graph have already been traversed somewhere in that path that I have seen so far. So therefore the new vertex must be going back somewhere here. So it must be one of the vertices already seen, so there must be a cycle. So there is a directed cycle, and since there cannot be a directed cycle, this cannot happen. Right? So this is a complicated way of proving something. It's called proof by contradiction. So you say assume that everything has a non-zero in degree, then I can find a path which is of arbitrary length, in particular of length n, which will visit n plus 1 vertices, and since n plus 1 vertices must repeat a vertex, there must be a cycle, and this cannot happen. Right? So this is why we will always have a starting point. We will always have a starting point which is an in degree vertex with a vertex with in degree 0. So this claim is now a fact, right? So that was a proof that we have a vertex which is guaranteed to have in degree 0. So in this particular graph, as we said, we have the vertices labeled 0 and 1, which both have no edges pointing into them. Now what do? Well, we list it out because we start from there. And once we list it out, we kind of pretend that it is no longer a constraint because it has been done. Right? So if it was a constraint for somebody, for example, if we look at vertex 4 for instance, right? So vertex 4 requires vertex 0 to be completed. But if I list out 0 saying 0 is done, now 4 has no longer any constraints because this constraint is gone. Right? So this was our claim, that as we go along, the constraints will go away until you can list out the later vertices. So if I delete that vertex that I just found and all the edges from J, what happens, right? So if I delete this and then I delete all the edges that point out of 0, then I'm left with a smaller graph in which there is one less vertex and a fewer edges depending on how many edges I had connected to that original vertex. But notice that in this process I have only removed edges from a directed graph, And if the original graph had no cycles, this must also have no cycles, because I have not put back any edge between two vertices which were not already connected. So what remains after this is again a DAG. So I take a DAG, I remove any vertex from it, it remains a DAG. It may not be connected for if I have done it badly, but at least it cannot have any cycles. So it will be directed and it will be acyclic, right? And therefore, by the same argument, in the new DAG, right, is after I believe this constraint has been satisfied, I must again have some vertex with in degree 0, right? So at every stage I have a DAG. Whenever I have a DAG, by that earlier argument, there must be a vertex within degree 0. So at every stage there is at least one vertex which I can remove. And I keep doing this, and after n stages I must have removed all the vertices. So this is why the procedure works, right? So we repeat this process until all the vertices are listed, and we are guaranteed that at every stage, start with a DAG, remove a vertex of in degree 0, I have another DAG. Therefore I have another vertex of in degree 0. Remove that, I have one more, and so on, right? So that's why this process is guaranteed to make progress and is guaranteed to exhaust all the vertices in my DAG. So the first step to implement this as an algorithm is to compute the in degree. So assume that we have the graph presented to us as usual as an adjacency matrix. Then we know that the incoming edges are in the columns, right? So remember that the row I has all the outgoing edges from I, and the column I has every entry of the form j comma I, which is an edge from j to I. So if I look at the column I, it has all the entries for the incoming edges. So if I just walk down column I and add up the ones, remember that this matrix has 0, 1 entries. If I just add up the ones, I will get the in degrees, right? So here we have got this graph, and by doing this one scan, although we can do it pictorially in this particular case, by doing this one scan, we can count the incoming arrows. So for instance, this has in degree 2 because there are 2 edges coming in. This has in degree 4 because there are 4 edges coming in. But this is not something we have to do with the picture. We can actually just mechanically do it using the adjacency matrix. So now that we have this, now we can compute. So we have an alternative, a second list in some sense, a list of in degrees of every vertex. We know in advance that there must be at least one of these vertices which has in degree 0. We don't know which one, but we can find it by just scanning down the list and looking for a 0. So we go down the list and we look for a 0, and perhaps we decide to pick. So there are 2 in this case, as we know, right? So we have both vertex 0 and 1. So let's suppose we choose to do this one. So remember, our procedure says list it out and remove it from the graph, right? So we list it out here. So the bottom is our list, and we remove it from the graph, right? So the edges which are now pointing out of vertex 1 have been removed, and in this process the targets of those edges in degree has reduced, right? So when I do this, I had an edge, I claim, like this. So this in degree and this in degree now will change. So when I remove that vertex, I must also simultaneously update the in degrees. I don't have to scan all the in degrees again. I only have to look at the row for I, right? The vertex I just deleted is I. I only look at the row for I, and every ij that I have as an edge, I look at the degree of j and I reduce it by 1. So in this case I had 1 to 2 and 1 to 7. So I go to vertex 2 and reduce its in degree by 1. I go to vertex 7 and reduce its in degree by 1. Now again I have a DAG, a smaller DAG. Again I must have a vertex at least 1 of in degree 0. Here I have no choice, I have only this one. So I remove that and list it out. And now again, these are the 3 vertices which were getting edges from the vertex 0 which I just deleted. So now I have to reduce their in degrees by 1. Now I have a wide variety of vertices with in degree 0 which I can enumerate next, because all of them depended on 1 and 2. So I pick any one of them, right? So for instance, I pick 3, the one in the middle, right? I pick 3 and I remove it, so I list it out. And now 3 was pointing in this direction and this direction. So this 2 will have to reduce and this 3 will have to reduce. So I reduce them. Now again I have 2 choices, 2 and 4. So perhaps I do 2 next. So I take 2 and now I reduce the in degree of 5 by 1. Right? Now I have these 2 candidates to enumerate next. So perhaps I pick vertex 5, right? And then I have to reduce the in degree of 6 by 1. And now maybe I do 6 next, okay? And then I reduce the in degree of 7 by 1. But I still cannot enumerate 7 because it has in degree 1, but 4 is left, with in degree 0. So I can enumerate 4 next, reduce the in degree of 7 to 0, and finally I can enumerate 7. Right? So if we look at our original graph, this is what the graph looked like. So what we have said is that we did this first, then this, then this, then this, then this, then this, then this, and then this. Right? So this is the sequence in which we enumerated it. Perhaps not the most obvious sequence that you would have thought of. We might have thought of doing it top down, so we would have done 0, 1, and then maybe 2, 3, 4, and then 5, 6, 7. But this is a valid sequence. Right? So what if we had adjacency lists instead of adjacency matrix? So we said in an adjacency matrix representation, we can find the incoming edges by looking at the relevant column. We look at column I and we have done it. In adjacency list, we only have outgoing edges, right? If I look at the list for I, it has only edges pointing out of I. So how do I get the edges pointing into I? Well, you don't do it in one shot, right? So for the column thing, you compute the in degree of I in one shot by looking at the column for I. Here you look across all the lists. So you'll start with vertex 0 and look at the list of things that 0 is pointing to. So 0 is pointing to, in this case, 2, 3, and 4. So what you will do is you will have separately in degree of 2, in degree of 3, and in degree of 4. So when I see this 2, I will do a +1 here. When I see this 3, I will do a +1 here. When I see this 4, I will do a +1 here. Now I come to 1, right? So 1 has outgoing 2 and 7. So now I'll do another +1 here, and in 7 I'll do a +1, and so on. So you basically scan all the lists from top to bottom, and for each outgoing edge you see, you go to the corresponding target in degree and increment it by 1. So even if you have an adjacency list, we can do a simple scan and update all the in degrees to start with. After that, it's only a matter of checking the in degrees as you're deleting them, so it doesn't matter whether it's an incoming or an outgoing. So we have the usual caveats as we had before, that is, if you're doing an adjacency matrix, everything takes order n time because you have to look at all the outgoing edges or all the things, whereas if you're doing something which is an adjacency list, you can do it in time proportional to the total number of edges. So to summarize, we've seen from the earlier lecture that directed acyclic graphs are a very natural way to represent dependencies, and one of the fundamental problems in such a situation is to find a feasible schedule, find a sequence in which you can perform the tasks or do whatever we need to do, which does not violate any of the constraints. So something must be listed before something that depends on it, right? So what we observed is that in any DAG, there has to be at least one vertex which has no dependencies. Okay? Something which in the graph version or the directed acyclic graph representing the dependencies has in degree 0. So we can list it because it has nothing that has to come before it. And eliminating a vertex from a DAG gives us back another DAG, a smaller DAG, possibly disconnected. Okay? So we could have a DAG, for instance, which looks like this. This is a DAG. So it says that I must do this, say this is my first task, and I must do this before 2 and 3. Now once I have done this, right, now I have a DAG which consists of just 2 and 3. So we might end up with a disconnected graph, but it's still without cycles. And therefore by the same logic, it must have something of in degree 0, and so we can keep repeating, and that's why this process works. Now the other thing to notice is that more than one topological sort is possible. So we saw that when we looked at that example of how to set up the room, we said that, for instance, tiling the floor and plastering the walls can be done in either order. And in particular, what happens is that when we end up with multiple choices for in degree 0 vertices, so if you look at our previous example, for instance, I could have started with 0 or with 1. We chose to start with 1. If we started with 0, we would have got a slightly different sequence. Similarly, we had a situation when we had 2, 3, and 4 all available to us with in degree 0. So we chose to do 2 first. We could have done 3 first. We could have done 2 first. We could have done 4 first. Right? So whenever we have multiple degree vertices with in degree 0, topological sort does not necessarily force us to take one or the other. We might choose to take the smallest one, in which case we get one particular ordering, but there are multiple orderings possible. Right? So this is the thing that we need to remember, that topological sort produces a sequence which is compatible, but this is by no means the only sequence. There are multiple topological orderings possible. In particular, if you have no dependencies, right? If I have all the tasks are independent, then any ordering is possible. So if I have, this is basically if I have n independent tasks, right, then I would have n factorial ordering. So the number of topological orderings can be very large. So we are not really interested in computing at this point the number of topological orderings. We are also interested in finding one of them.